Hey guys, this is Lego Masa 99 again today, and today I'm going to be attempting to explain to you guys how the Redstone Computer 3.0 works. Now, this is actually just about 2 years old to the day, and I know a lot of you guys are very curious about how it works, and I've had requests from people that requested me basically to go more in depth to how this whole thing works and how it specifically works and all of the little nooks and crannies with it and everything. So that is going to be this video today. I'm going to basically talk about how everything in this computer works, basically as specific as it gets, or not that specific, but you'll have a much better idea of how the specific components of this computer work and how it all comes together. And if there's basic problems with it, then you'll know a general idea of what's going on instead of just hoping that it works or doesn't work, because it is a very big machine. It's made of thousands of different little parts that all work together and that are controlled by you and the program and everything. So without further ado, let's go ahead and get into the video. Now this is going to be a pretty long video, so yeah, just buckle up. This is going to be an interesting one. Actually, before we start this video, I wanted to mention that I've also created diagrams that basically depict what this computer does and the more advanced conceptual technical stuff. So yeah, just a diagram of the computer and a data flow and that kind of thing. So if you guys maybe don't understand what I'm saying, or it's too tricky, or my words aren't coming out right, which happens often, you can just look at the diagrams and hopefully those will give you a much better representation of what actually goes on through this whole redstone mess. Alright, so the first thing that I will get into to explaining is the UI control panel. Here it is, the UI. And basically, I'm going to start here because that's what most of you guys are going to be interfacing with the most. So yeah, so basically we will start off, I guess, first with the power controls. Alright, now I'm going to talk about the program settings here. And as you can see, there are three different, I guess, sub-menus, sub-options of program settings. So the first one here, basically what to do during the program, so program execution settings. And the first one here is clearing the RAM and the UI outputs on shutdown. And basically, when this is turned on, there's basically an AND gate here for the clearing the RAM. And when the computer off button is hit, if this switch is on, it'll send a signal down this blue line right here. And this blue line runs all the way down to, what do you know? It runs all the way down to the memory, the RAM, all the way down here. And this line just basically wipes the RAM of any data that is present in it. And then the other option that is listed on the sign, which is clearing the UI outputs on shutdown, the same thing happens, except another signal is sent to the peripheral registers. The output registers, basically. And I'll go more in depth into it later, but basically there are registers here that save the values that are pushed onto the displays here in the output. So when that switch is flipped, it'll reset those registers as well. And reporting program exceptions to I/O. And the program exceptions are the shift overflow and the shift underflow flags. And that is basically just another simple AND gate. And that switch right here hooks up to this line right here, and it's basically just a very simple AND gate, so that when that switch is flipped, the signals will be able to propagate from the different ALUs to tell the user whether a shift overflow or a shift underflow has occurred. And if you don't know what those are, I explain it in my main video. Alright, so now we're going to talk about the clock selector. And now this is actually pretty simple, although it might not look so simple. So basically we have 3 bits here that run into a decoder, which is right here, and this decodes 0 through, or I guess there's 8 different options, which is 7 plus 1, so basically 0, 0, 0 all the way up to 1, 1, 1, so you have 8 options, and based on what assortment of switches you flip, it'll give out one output here on this decoder. So as you can see, this torch is currently on, and only one of these torches will be on at any given time to select the speed that the user wants the computer to run at. And then that signal will propagate up here, and there's another AND gate up here with these torches and the torches down here. And this basically turns on when the RS NOR latch for the computer power state is set, so it's on. And basically what will happen is that when this turns on, the specific torch here that's selected will turn off. So this will, for example, since we have this selected, this line will turn off, and then it'll enable these clocks to run, and these clocks are set to the different speeds that are listed on these signs right here. So all these different tick speeds are basically programmed here, and then these signals, the clock is sent out on each one of these repeaters, but only on one repeater per per clock. So the clock signal for this line would come out on this repeater right here, and then for the next one to come on this repeater. So then one clock signal will be generated from this whole machine, and it'll run down this clock line, and then go into a monostable circuit, and then run down the main clock line, which is right here, and this runs all the way down to the computer's clock input, which is like the pulse of the computer, and it allows everything to run it all. So that's basically how that works. Alright, now the last part of the program settings, the core toggles. Basically what happens is that whenever you flip one of these switches, as you can probably see here, it propagates all the way down, and then it propagates to these lines right here. Now these are the core enabler lines, I like to call them. They're labeled right here. Enable core 1, core 2, core 3, and core 4. And basically each one of these lines hooks up to AND gates that are on the program memory registers, which are right here. These green registers that are really long. And basically it either allows or blocks the clock signal to update these registers. And updating these registers is basically what allows the program to run. So let's see here. Since we have core 1 enabled, if we look here, this piston is up, and as you can see, the signal here can flow through, and then it goes ahead and updates. Or this is a different line, but for these main two registers right here, it allows, as you can see, it also allows the clock line signal to update those registers every single clock update, so that the computer can continue. But if the cores are disabled, like these three here, if we look, so here are this specific core's register update lines. They are blocked. So when the clock signal tries to go through, it will not go through, and it will not read anything from the program memory. So that is basically how the core enable lines work. Alright, so I will get into the user input and or I guess just both segments of this user input section here of the UI later, as they are input peripherals. So we'll get into that later. And now I guess I'll get into the miscellaneous controls. Now these two are just, they don't do anything. Now this switch here turns on the RNG, random number generator, and this just runs down to the random number generator, which is right here, and this just runs on a set of random clocks to generate a seemingly random signal. And yeah, this is also an input peripheral, which I will explain later, and that's how that works. And if this switch is not on when you run a program and the program requests to use the RNG, it'll always get a series of zeros out because it's not on. So if you're writing a program or running a program that makes use of the random number generator, make sure that the switch is on. But it does induce a little bit of lag. Well, I mean, I'm not getting that much lag right now at 400 FPS, but yeah, just make sure of that. And then clearing the RAM here, this button just hooks up to the blue line that I showed a little bit earlier with the program settings. It just hooks up to the same line and goes ahead and clears the RAM for you. So if there's a reason you want to manually clear the RAM, you can do it from here. And this button just teleports you to the debugger center, which gives you much finer control of all of the computer power states and commands and all that kind of stuff. And then this just goes back up to the main panel. And then here's the computer tractor. If you're into that, it's just a rail line that runs across, and that's in the world download. So yeah. Alright, so now I'm going to go ahead and get into these line of code for cores, basically right here. Now these are just indicators that display which line of code each core is on when it's running. And each one of these, each one of those indicators hooks up to the core's line of code register. which is right down here, or it's not a register, it just hooks up to the line of code that it's currently on to the decoder as well. So this comes from the go-to system, which I will explain later. And so each one of those indicators hooks up to that, so you know exactly what's going on with the core at any given time in the program. And the last thing to explain here is the program output panel. I already explained to you the shift overflow and shift underflow, and these four here are just indicators that can be turned on by the program. So when you're writing it, and that's where they will end up there. And that is basically everything about the user input panel and how it works, or the UI rather. Alright, so now that I have explained the UI panel, I want to go ahead and explain a little more conceptual, or some of the more conceptual stuff of this computer. And I want to go ahead and explain the data flow of this computer, how this computer moves data around. And yeah, so it's going to be kind of a little bit tricky, but try to stay with me. Alright, so data flow for this computer, basically, we start off at the program memory. And the program memory gives instructions to the computer on what to do, pretty obviously. And so it starts off that when you turn the computer on, this line right here will turn on for every core. There's one line for each core. And this basically loads a 1 into the line of code register here for the program memory, and that basically loads the first line of code. And each line of code gets loaded through these registers every single clock cycle. So once it gets loaded through the registers, it gets decoded by a series of decoders that are hooked up to it, and it runs all throughout these registers. And then those decoders basically provide operations for the computer to do, and then the computer goes ahead and executes those operations. And that's how that works. And now for the actual flow of data, I guess, starts off, it could either start off in the, or I'll just start off here at the RAM. So it goes in a full circle, and I'll explain that. So data in the RAM can be written to RAM by the instructions, and that comes down this line right here, or this main bus. And actually, I should explain this. This main bus right here hooks up basically to every single component of the computer. This bus right here, this gray one, this is called the master output bus. Or at least I have dubbed it that. And every single output and input device or peripheral is in some way hooked up to this master output bus. And this master output bus runs throughout the whole length of the computer, and it runs all the way down to the RAM. And the RAM is where the data can be stored and basically remembered, so that the data doesn't disappear in the next clock cycle. So once the data is written to RAM, it can be read out from RAM again, and this RAM has a dual read system, so you can read 2 bytes of RAM at a time, and it's very efficient. Instead of reading 1 byte and then saving it somewhere, and then reading the second byte and then saving it somewhere, and then doing an operation with both of those bytes. Like an example with one of the ALUs and one of the cores. And yeah, so you can read, dual read 2 bytes of data from RAM at a time, and it runs to the ALUs in each of the cores. So if we follow these lines, it goes up into the inputs of the ALUs of the cores, and those inputs are right here. So it goes to each input A and B, and the ALUs basically manipulate that data somehow based on the instructions given from the program memory, the instruction set, and then they output more data in the form of, let me find a register up here, in the form of an output. So that's an 8-bit output. So you get basically the ALU takes in 2 bytes of information, it outputs 1 byte, and also outputs 5 bits of conditional information. So as you can see up here, shift underflow, shift overflow, A equals B, A is greater than B, and B is greater than A. So it outputs those for conditional purposes and branching and that kind of thing, which I'll go into more depth in a little bit. And then the output from the ALUs hooks right back up to, you guessed it, the master output bus. And then once it goes to the master output bus, then it loops back into the RAM to be saved and manipulated again. And that's basically the basic data flow of the computer. And yeah, So as I mentioned, all of the output and input peripherals are also attached to the master output bus in some form. So as you can see here, we have a split off from the master output bus that goes to the decimal display register and the binary output register. And then we have here the pip and pop ports. So they are both hooked up to the master output bus. Each of the outputs from the ALUs is hooked up to the master output bus. We have the user input, the 8-bit user input, or 1 byte, is also hooked up to the master output bus for the set that data can be transmitted throughout the computer. And then the random number generator is also connected to the master output bus. And there is actually also, it's basically, I was going to say something, but it's not really relevant. So that's basically the master output bus and the general data flow of this computer. Alright, so now that the data flow of the computer is out of the way, I want to go ahead and explain how the various different parts of the instruction set actually work and how they are built and all that kind of thing. So first off, we'll go ahead and start on the go-to section here. So in the go-to part of the instruction set, there are 15 bits here, I'm pretty sure, 15, yep. And the first 5 bits are for go-to false, so what line of code the computer will jump to when the condition is false. And this is when 5 bits for true, and this is the condition itself. So after it's loaded into the program register, we basically have a multiplexer right here that switches to select which line of code to jump to, and this merges into the line of code decoder, which is hooked up to the line of code indicator on the UI. And this basically loads, this decoder here loads the next line of code to use. And this multiplexer here, the status that it's in is determined by the conditional, the condition that you select. And so that goes into a decoder. Then there's different options here, and there's basically AND gates. As you can see right here, there's 2 different signals powering off this torch. So, like, actually, it's a better example if I go over here. As you can see, this is for shift overflow, I'm pretty sure. So if you have the shift overflow condition selected, it would be off like that. And then if the shift overflow condition was actually true, based on the 5-bit conditional register that is updated whenever you do an ALU operation, which is up here, if it is actually true, then it will go ahead and turn off the other side, and then this torch will turn on, and then the multiplexer will switch to go to the go to true, to load the go to true line of code. Excuse me. So that's how the go to system works. It's pretty basic, but it's also pretty complex at the same time. Alright, so the next part of the instruction set that I want to explain is basically the rest of it. So here we have 8 bits of data from each core that basically go into the inputs here, and this eventually just runs all the way back to the master output bus, and this connects to the ALU input. I'm pretty sure it hooks up to ALU input A on every single core, so you can feed in data that way. And these 4 bits here are for, I'm pretty sure it is the RAM read or the RAM write. I'm not too sure, but actually, let's go take a look. Okay, so it hooks up to RAM write, this cyan line here. It's kind of crazy. I don't even know what it means, but it's all right. So these 4 cyan bits here are the RAM writes, and that hooks up to this 3-way multiplexer right here. I'll explain that in a minute. But on its default state, it'll go to the write lines here for RAM, and it'll select here. It's hooked up to another decoder, and it'll enable 1 byte of RAM at a time for write access from the data that goes through here. And the next 4 bits are the RAM read right here, and this basically runs here into this section here. And now this here hooks up to read A, I'm pretty sure, down here, and then read B is in the top. So the way this works is that when you have dual read selected, the multiplexer will switch from switch the role of the cyan right here, and that'll go from write to read B, which should be right here. So the pistons will flip, and then And this will act as a second read, and then it'll hook up to the read buses here so you can read another byte of data. And next we have the opcode right here. So this is the 5-bit section where you put in the opcode that you want. And as with most things for this instruction set, it is hooked up to a decoder. And here's the opcode decoder for this core at least. And it has all the different operations you can do with opcodes. And it just connects to whatever device in here it needs to be connected to perform the operation. So for example, ALU add, this sends a signal to the ALU to select the addition operation, which I will explain how this all works later, but this signal runs all the way up to the ALU to select the addition operation, and then same for the subtract and compare, not, and then the bit shifting, all that stuff. So that's just basically how the opcodes are selected and determined. And then we have here the 2 bits here that represent either, pretty sure I have it right here, yeah, single or dual read select, and then read AB select. So these both hook up to the this multiplexer right here, and the let's see here, the dual read line connects to switching these 2 sets right here. So then the write will be disabled and the second read will be enabled. And then for the read A and the read B, it'll just toggle, I'm pretty sure, to these 2 right here to see whatever happens. Yeah, so that's pretty much how that works. And the last part to explain here, but definitely not the least, it's probably the most complicating out of all of them, is the extension bits right here, these 3 bits. Alright guys, so the last thing to explain here is the extension data, these 3 bits right here. And basically what this is that it allows you to select certain options based on the opcode that you select. So this is used for 3 opcodes, I am pretty sure. If we go back up here, it is used for the register flush opcode and the IO output and IO input opcodes. And basically you use this right here to select which specific option you want to do with that opcode. So for example, the register flush opcode, you would select there which register you want to flush. And same thing for IO output and IO input. Like for the IO output, you would put in the extension data what peripheral you want to output to, or yeah, that you want to output to, and that kind of thing. And the way that it works is that, as with most things here, there's a 3-bit decoder for our extension data, and then that basically goes into this thing, and it's kind of a complex AND gate. That's basically all it is. It's just really jumbled up. And like an example here, let's see here. Like for the IO input user input, this will turn off when the IO input opcode is selected. And then if this first bit here, so 1, if a 1 was put in the extension data, it will turn these torches off. So basically, when both of those conditions are met, then this is turned off, and then the signal propagates all the way to, and I just lost it. Where does it go? It goes here, and it goes down this line all the way to the IO input for user input, or at least it should. Yeah, there you go. It goes to the IO input line. Or did it? Yeah, it's this line right here. So yeah, anyways, it's a little bit messy. Even I got lost in the wiring, but yeah, so that is basically how the extension data works. And also, I just remembered, you also can use it to, oh yes, for the indicators as well. It's the same thing. So that's how it works, so you can select different options for the opcodes. Alright, so now that I have covered the instruction set and how it's all decoded and how it's all processed, the last thing that really needs to be covered is how the ALU works in for each core. Now, basically, as I mentioned earlier, there are 2 inputs here, input A and input B. And if you just look here, there's basically a master ALU bus that runs through the entirety of the ALU. As you can see, it kind of just snakes up here and goes around. It's 3 layers tall in this case for this computer. And I think I'm on the wrong one. Okay, right here. So what happens is that there is an AND gate right here, or just a gate, I guess, that blocks the data from going through unless an ALU operation is being performed. So we follow this line up here. Let's see. Right here. All right. So this line gets activated whenever an ALU opcode is selected. So if one of the 6 ALU opcodes is selected, then these pistons will retract, allowing the data to flow through into the ALU. The conditional register will be set so that data can be written to it, and the output register, as you can see here, is also set because of that signal so that data can be written to it. Now once that happens, the data flows through the ALU and does its necessary calculations. Now what I mean by that is that there are certain, components to the ALU. And as you can see here, they branch off the main bus. So there's one thing over here, there's another thing over here. If we go up, there is something right here, there's another thing right there. And basically, these are just the operations that the ALU can do. So this right here is an adder. And then over here is a subtractor. And if I didn't give proper English, I'll say proper English. Yeah. So this is proper English's adder design. And I gave him credit here, and I think I gave him credit in the original video, but this is one of the best adders that I've seen in a while. So, but new developments are always being made all the time. So, but anyways, there's an adder, and there's a subtractor. It's the same design, it just has 2's complement applied to it, as you can see. And then you have the, I think this is the comparator right here, and this hooks up right to the conditional status register. This is the NOT operation, and then we have bit shift left and bit shift right on the top here. And basically what happens is that each of the these components here, okay, I got a little lost. Okay, I think we're up here. Yeah. All right. So each of the components, basically, once the data is allowed to go through, it'll be manipulated by every single component, and then it'll the output that will be selected for the final output is chosen by the ALU opcode. So what I mean by that is that when the data flows through, the A and B will be added and subtracted and compared, and a NOT signal will be applied to it, and it'll be bit shifted left and bit shifted right all at the same time. But the way the result from the ALU as a whole is selected is from these lines right here, this blue gate. So let's say I selected an ALU add operation. I'll just go ahead and turn this one on. If we look here, this gate then gets powered. So the result from the add operation can be sent, I'll turn this off, can be sent up to the ALU master output bus, I guess. It's the master output bus of the ALU. It's this gray bus right here. And basically it connects every single output of every single component together. So as you can see, we have the NOT here, we have the subtractor down here, and that hooks up to the ALU master output bus as well. And every single operation hooks up to this one bus, and it all gets routed to the output register. So that is basically how all the computations work in the ALU, so that it's efficient instead of waiting for all of it to be routed at the same time. So yeah, that's basically how the ALU works simply. And each of the components does their own thing, as I mentioned earlier. And yeah, that's basically it. And then once that the output is output into the output register, then it goes onto the master output bus and follows the general data flow of the computer. So as you can see, it's hooked up to the master output bus, and then it runs all the way to RAM, or it can be routed to the output peripherals or anything else that the program wants to do. So yeah, that is basically how the ALU works and how it is integrated into the rest of the computer. And that's not just for one core or for one ALU, that is the same principle for every single ALU and core. What I just explained, it applies for all 4 cores. And yeah, I don't think there's really anything else much to cover. So yeah, with that, guys, that wraps up the video. I hope you guys found it somewhat informational, as that was the objective of the video, but hopefully it was a little bit interesting. You guys learned some stuff, and as I said, there will be diagrams that will be provided in the description so that you can make more sense of this huge mess. And yeah, I'll see you guys in the next video. Thank you for watching. Bye bye.